Hey, I think we can start now. So today we will start with this paper presentation. Lois, who was previously a postdoc in our group and he is currently director at Galicia Supercomputing Center, will tell us about this paper on RowHammer. And in the second part of the meeting, we will go over the status of your projects, and yeah, you will give us like 5 to 10 minutes project updates. Okay, great. So yeah, you can start, Lois, when you're ready.
Okay, Hassan, thank you for the introduction. Yeah, I'm Lois Orosa, and today I will be presenting this work, a deeper look into RowHammer's sensitivities, experimental analysis of real DRAM chips, and implications on future attacks and defenses. So this is a DRAM module used as the main memory of many systems. A DRAM module consists of multiple chips, each of which contains multiple banks. Each bank is composed of multiple subarrays, and within each subarray, there is a two-dimensional array of DRAM cells. These cells are organized into rows that are selected using word lines, and the cells are connected to a row buffer via bit lines. This is a simplified diagram of a DRAM cell, where the data is stored as capacitor voltage and accessed through the access transistor. A DRAM cell inherently exhibits several charge leakage paths and requires to perform refresh operation to restore the capacitor voltage with a time period called refresh window. To access a DRAM cell, the memory controller must first open or activate the row to fetch the row's data into the row buffer. The read and write requests targeting the row are serviced from the row buffer. After all requests are serviced from the row, the memory controller must close or recharge the row in order to begin accessing data from another row. Due to the increase in cell-to-cell interference as a result of aggressive technology node scaling, rapidly activating and recharging a DRAM row can result in bit flips in physically adjacent rows. Continuing to access the same row results in even more failures in nearby rows. This phenomenon is known as RowHammer. We refer to the rapidly accessed row as an aggressor row and the rows containing bit flips as victim rows. Now I will quickly summarize our work. Denser DRAM chips are more vulnerable to RowHammer, and understanding RowHammer is critical to find effective and efficient solutions. However, no rigorous study demonstrates how this vulnerability varies under different conditions. In this work, our goal is to provide insights into three fundamental properties of RowHammer that can be leveraged to design more effective and efficient attacks and defenses. These properties are DRAM chip temperature, the time that an aggressor row stays active, and victim DRAM cells' physical location. In this study, we test 272 real DRAM chips of DDR3 and DDR4 modules from 4 major manufacturers. Based on our analysis, we draw 6 key takeaways lessons from 16 novel observations. Among these, we highlight that a RowHammer bit flip is more likely to occur in a bounded range of temperature if the aggressor row is active for a longer time, and in certain physical regions of the DRAM module under attack. Based on our findings, we propose several improvements and show that our novel observations can inspire and aid future work on crafting more effective attacks and designing more effective and efficient defense mechanisms. So this is the outline of the talk. Let me begin with our motivation and goal. RowHammer is a DRAM reliability and security problem. Denser DRAM chips are significantly more vulnerable to RowHammer, such that the minimum activation count to observe a bit flip has reduced by more than an order of magnitude in less than a decade. Recent works have demonstrated that many defense mechanisms are becoming prohibitively expensive for future DRAM chips. A deeper understanding of RowHammer is the key to overcome this challenge. However, no rigorous experimental study demonstrates a set of fundamental properties of RowHammer to find effective and efficient solutions. Therefore, to enable RowHammer's safe operation with future DRAM chips, it is critical to gain insights into RowHammer and its fundamental properties. Our goal in this work is to provide insights into three fundamental properties of RowHammer: temperature, aggressor row active time, and victim DRAM cells physical location. By doing so, we are enabling research to find effective and efficient attacks and defenses. Let me quickly explain our experimental methodology. We use two FPGA-based experimental setups for DDR3 and DDR4 DRAM modules, both programmed with a modified version of SoftMC. We control the chip temperature using a pair of heaters connected to a temperature controller. These infrastructures provide fine-grained control over DRAM commands, timing parameters, and temperature. To characterize our DRAM chips at worst-case conditions, we take two measures. First, we prevent external sources of interference such that our test can run consistently as desired and without interruptions. To achieve this, we disable DRAM refresh to avoid refreshing rows during a RowHammer test, DRAM calibration events to minimize variation in the test timings, and RowHammer mitigation mechanisms to ensure that we can directly observe circuit-level bit flips. We also ensure that our tests complete in less than a refresh window to prevent retention failures from interfering with our results. Second, we issue the worst-case access sequence for inducing RowHammer bit flips based on observations from prior work. Using these observations, we test each row worst-case vulnerability to the RowHammer by repeatedly activating the two physically adjacent rows as fast as possible. In our characterization, we test 272 real DRAM chips from 4 major manufacturers that implement DDR3 and DDR4 DRAM standards, and with different densities, die revisions, and chip organizations. We provide more details about the chips we test in our extended version of the paper published in arXiv. Let's begin with our first analysis, that is temperature. This analysis provides two key takeaway lessons. The first is to ensure that a DRAM cell is not vulnerable to RowHammer. We must characterize the cell at all operating temperatures. And second, RowHammer vulnerability tends to worsen as DRAM temperature increases. However, individual DRAM rows can behave differently from the dominant trend. We analyze the temperature levels a DRAM cell is vulnerable to RowHammer. We observe that there exists a lower and upper bound of temperature. A DRAM cell experiences bit flips only in this bounded range. But we do not observe any bit flips out of this range. We call this range vulnerable temperature range. This table demonstrates the fraction of DRAM cells that experience bit flips at all temperature levels within their vulnerable temperature range. You observe that more than 98% of vulnerable cells across all 4 manufacturers exhibit this behavior. Therefore, we conclude that most DRAM cells are vulnerable to RowHammer through a continuous temperature range. This figure shows the population density of cells clustered based on their vulnerable temperature range. The x-axis and y-axis shows the lower bound and the upper bound of a DRAM cell's vulnerable temperature range. The color scale and the percentage values shows the fraction of cells for a given temperature range. For example, 0.4% of the cells are vulnerable to RowHammer only between 55 and 60 degrees Celsius, meaning that these cells does not observe any bit flip at 70 degrees or 50 degrees or 45 degrees. They only observe bit flips from 55 to 60 degrees Celsius. Another example is that 0.5% of the cells experience bit flips only between 70 and 85 degrees Celsius, as we see in the figure. We conclude that different DRAM cells are vulnerable to RowHammer within specific temperature ranges. Here are the results for all 4 manufacturers. We make 2 observations from this figure. First, we observe that a significant fraction of vulnerable DRAM cells exhibit bit flips at all tested temperatures. In this example, is from 50 to 90 degrees. For example, almost 30% of the cells from manufacturer D experience bit flips at all temperatures we test. Second, we observe that a small fraction of cells from all 4 manufacturers are vulnerable to RowHammer only in a very narrow temperature range. For example, 0.2% of the cells from manufacturer D experience bit flips only at 70 degrees Celsius. Next, we study the impact of temperature on DRAM rows. The figure shows how the number of bit flips in the victim row changes as temperature increases. The x-axis shows the increase in temperature, and the y-axis reports the variation in bit flip counts normalized to the mean value at 50 degrees Celsius. We observe that more cells experience bit flips with increasing temperature. We repeat this analysis for all 4 manufacturers. We observe that the bit error rate increases with temperature in modules from 3 manufacturers, while it exhibits an opposite trend in modules from manufacturer B. We hypothesize that this happens due to different characteristics of charged trap error mechanisms in different manufacturers. Please refer to our full paper for more details. Our main observation from this figure is that the DRAM row's bear can either increase or decrease with temperature depending on the DRAM manufacturer. In the paper, we also analyze the variation in HC first, the minimum activation count at which a victim row experiences a bit flip, and make 3 observations from this analysis. First, just like the bit error rate, DRAM rows can show either higher or lower HC first when temperature increases. And second, HC first tends to generally decrease as delta temperature increases. And third, delta HC first tends to be larger as delta temperature increases. We have more details in the full paper. Next, we investigate the variation in RowHammer vulnerability with the time and that an aggressor row stays active. This analysis provides 2 key takeaways. First, as an aggressor row stays active longer, victim DRAM cells become more vulnerable to RowHammer. And second, RowHammer vulnerability of victim cells decreases when the bank is precharged for a longer time. To perform this analysis, we conduct 2 sets of experiments. In the baseline, we hammer rows A and B as frequently as possible. In the first set of tests, we increase the time that an aggressor row is active. And in the second set of experiments, we increase the time that a bank is precharged. This plot demonstrates how bit error rate varies when aggressor row active time increases. We observe in this figure that as the aggressor row stays active longer, more DRAM cells experience RowHammer bit flips. We observe the same trend on modules from all 4 manufacturers. In this plot, we investigate the variation of HC first, the minimum activation count to observe a bit flip, with increasing aggressor row active time. In this case, we observe that DRAM cells experience bit flips at smaller activation counts when aggressor row stays active longer. We observe the same trend on modules from all 4 manufacturers. Based on our observations on the bit error rate and HC first, we conclude that as the aggressor row stays active longer, more DRAM cells experience RowHammer bit flips, and they experience RowHammer bit flips at lower activation counts. In the paper, we also investigate the variation in aggressor row active times effect across DRAM rows and the effect of increasing bank recharge time. We make 3 observations from this analysis. First, as the aggressor row stays active longer, the RowHammer vulnerability consistently worsens across all tested DRAM rows. Second, as the bank stays precharged longer, fewer DRAM cells experience RowHammer bit flips, and they experience bit flips at higher activation counts. And third, this reduction in RowHammer vulnerability is also consistent across all tested DRAM rows. We have more details and analysis on the paper. Our third analysis is about spatial variation. In this analysis, we investigate how the RowHammer vulnerability varies based on a victim DRAM cell's physical location. We have two key takeaways from this analysis. First, the RowHammer vulnerability significantly varies across DRAM rows and columns due to both design-induced and manufacturing process-induced variation. Second, the distribution of HCFers exhibits a diverse set of values within a subarray, but similar values across subarrays within a DRAM module. To do this analysis, we first investigate how HCFers, the minimum activation count to observe a bit flip, varies across different DRAM rows sorted by reducing HCFers value on the x-axis. Each curve in this plot represents a different DRAM module. You observe that HCFers values, and thus the RowHammer vulnerability, significantly varies across DRAM rows as we highlight here. This significant variation can be observed on modules from all 4 manufacturers. Zooming into the most vulnerable DRAM rows, we observe that the most vulnerable 10% of the rows experience bit flips at activation counts about half the HCFers of the other rows. Therefore, we conclude that a small fraction of DRAM rows are significantly more vulnerable to RowHammer than the vast majority of the rows. To investigate how the RowHammer vulnerability varies across columns, we generate a heat map plot. A heat map plot of bit error rates across columns and chips. What we observe is that bit errors concentrate on certain DRAM columns more than others, implying that certain columns are significantly more vulnerable to RowHammer than other columns. To further investigate the variation across columns and chips, we cluster each DRAM column based on its RowHammer vulnerability on average across DRAM chips and the variation in its vulnerability across DRAM chips. This plot shows the population density of DRAM columns exhibiting a level of RowHammer vulnerability and variation across chips. For example, 16.7% of DRAM columns exhibit a higher RowHammer vulnerability across all chips, indicating design-induced variation across columns. In contrast, more than 30% of DRAM columns exhibit a high variation in their RowHammer vulnerability across chips, indicating manufacturing process-induced variation. Here we see the same analysis for the 4 manufacturers we test. You observe that there exist columns with very low and very high variation across chips from all 4 manufacturers. Based on this analysis, we conclude that both manufacturing process and design affect a DRAM column's RowHammer vulnerability. In the paper, we also analyze the variation across rows in a subarray and across subarrays in a DRAM module. We make 2 observations from this analysis. First, the most vulnerable DRAM row in a subarray is significantly more vulnerable than the other rows in the subarray. And second, HCFers distributions of subarrays within a DRAM module are significantly more similar to each other than those of subarrays from different modules. We have more analysis in the paper. Now I will explain the implications of our observations on future attacks and defenses. We believe that our observations can be leveraged to craft more effective attacks and also design more effective and efficient defenses. In the following slides, I will explain several examples for these implications. In the first example, for an attack improvement, the attacker manipulates the DRAM module's temperature to increase the RowHammer vulnerability of the cells that store sensitive data. you observe that DRAM cells are vulnerable to RowHammer in a bounded temperature range, right? So this range is called vulnerable temperature range. So, for example, let this range be from 50 to 70 degrees Celsius for the victim cells. To attack the cells within their vulnerable temperature range, an attacker could heat up the chip if the current temperature of the cell is below 50 degrees, or cool down the chip if its current temperature is about 70 degrees Celsius. In the second attack example, the attacker uses RowHammer to understand the DRAM chip's current temperature. As an example, more than 76% of the vulnerable cells experience bit flips above 70 degrees Celsius for manufacture C. Focusing on these cells, an attacker can identify abnormal operating conditions that might occur in a data center during its peak hours. This information can be used to trigger an attack when the data center is under pressure. If it is important to measure temperature precisely, the attacker can focus on a smaller set of vulnerable cells that experience bit flips only in a narrow temperature range. For example, 0.4% of vulnerable cells experience bit flips only at 70 degrees Celsius in manufacture C, but not at 65, not at 75. So, using these cells, an attacker can precisely detect the temperature and trigger an attack accordingly. In the third example, an attacker can leverage the effect of Aggressor row active time. In this scenario, instead of activating Aggressor row as frequently as possible, the attacker can keep Aggressor row active for longer time. Based on our analysis, AC pairs reduces by 36% on average with the proposed access pattern. With this reduction, an attacker can bypass RowHammer defenses that do not account for this reduction. Yeah. I will also explain two improvements for defense mechanisms in this slide, but you can find more in the paper. So the first improvement leverages the variation across rows. We observe that 90% of the rows do not experience bit flips until the activation count reaches the double HC1st of the 10% of the rows. Therefore, we can reduce the aggressiveness of the defense mechanisms for 90% of the rows, which can reduce the area overhead of state-of-the-art defense mechanisms, block hammer and graphene, by 33 and 80% respectively. The second example leverages the variation in RowHammer vulnerability with temperature. We show that DRAM cells experience bit flips in bounded temperature ranges. To avoid bit flips, a DRAM row can be disabled when its cells are vulnerable to RowHammer at the current operating temperature. We propose more defense improvements in the paper, and I will briefly mention in this slide. First, leveraging the similarity across subarrays in a DRAM module can reduce the module's profiling time for RowHammer errors. Second, monitoring and limiting the Aggressor row active time from the memory controller can reduce the RowHammer vulnerability and make defenses more efficient. Third, ECC schemes can target the non-uniform bit error distribution caused by design-induced variation across DRAM columns. And fourth, cooling DRAM chips can reduce overall bit rate. Please refer to our full paper for more details on both attack and defense improvements. To conclude, I will come back to the first slide. So, denser DRAM chips are more vulnerable to RowHammer. And understanding RowHammer is critical to find effective and efficient solutions. However, no rigorous study demonstrates how this vulnerability varies under different conditions. In this work, our goal is to provide insight into three fundamental properties of RowHammer that can be leveraged to design more effective and efficient attacks and defenses. These three properties are DRAM temperature, the time that an Aggressor row stays active, and victim DRAM cells' physical location. In this study, we test 272 real DRAM chips of DDR3 and DDR4 modules from 4 major manufacturers. Based on our analysis, we draw 6 key takeaways, lessons from 16 novel observations. Among these, we highlight that a RowHammer bit flip is more likely to occur in a bounded range of temperature if the aggressor row is active for a longer time and in certain physical regions of DRAM module under attack. Based on our findings, we propose several improvements. We believe and hope that our novel observations will inspire and aid future work on crafting more effective attacks and designing more effective and efficient defense mechanisms. This concludes my talk. Thank you for your time. If you have any questions, I'm happy to answer them.
Thanks for the talk, Lois. There's one question on YouTube. Maybe we can start with that one.
Okay.
Are there significant temperature differences between cells on a DRAM chip?
Oh, that's a good question. So we don't know. We don't have a way to measure the temperature of individual DRAM cells, basically. So we basically cannot know that.
Okay, but intuitively, can we say something like regions of DRAM that are more frequently accessed may heat up more than the other regions?
Yeah, that makes sense actually. And yeah, a DRAM row can be divided in subarrays. Different subarrays could have different temperatures, maybe. Yeah. And different regions could have definitely different temperatures, as you said, depending on the frequency of the access. That's probable, but we don't know how much temperature difference are between those, because simply we don't have the tools to measure those temperature difference. Could be large, could be very small. So actually, we really don't know.
Okay. Are there any other questions? You can just speak up if you have questions for Lois, or you can write it on the chat.
Yeah, if you have questions or suggestions, if you can, looking at these observations, if you have any idea to improve any defense or attack mechanism, that would be great, actually. We draw some suggestions, but probably there are much more. Yeah.
So one question, just out of curiosity, you have, I mean, this is really interesting. I think these vulnerabilities of DRAM chips that you have investigated here and potential defense mechanisms. Now, I just, it's maybe an off-subject question, but like now you're some director of a data center. Just wanted to ask if kind of your knowledge somehow flows into that practical role. Are you like implementing some defense against that, or have you experienced attacks using exploding RowHammer? Maybe this is hard to answer, but would be interested to hear how kind of those two roles combine there.
But you mean if we are implementing something in our supercomputing center?
Yes.
So I just arrived like 20 days ago.
Oh.
So we didn't have even the time to put these issues on top of the table, but certainly this could be really, really interesting to do. I have that in mind, but yeah,
like
I will keep you updated about that.
Yeah, sure. But so I just wanted to also understand these RowHammer vulnerabilities are something that is also relevant to something like a supercomputing center. Yeah,
sure. This is relevant to all DRAM modules in the world as far as we know, and the RowHammer vulnerability worsens with when the technology node scales, right? Because everything is closer together, and this is a bigger issue. Although manufacturers are trying to mitigate this issue, there are many papers like this one and other ones that demonstrate that the problem is still there. So
still there, okay, yeah. Oh yeah, that's really interesting. Yeah, cool. Thanks.
Okay, great. I guess then we are done with this first part of the lecture. Yeah, thanks everybody for attending this lecture, and then we will continue with the project updates, but that will happen off the live stream. So we are gonna end the